Oscillations Lab 4. The purpose. The purpose of this lab is to examine the oscillations of a spring through tracker and compare a created computational model that will compute the energy changes and the position model that can be used on real-world examples such as the behavior seen in extreme rope sports. The importance. The momentum principle is utilized on a real-world example, the energy principle is utilized on a real-world example, and the computational model is created to predict position and energy change. The momentum principle. So we have F net equals mass times acceleration, and the acceleration can be rewritten as the change in velocity over change in time. This can then be used to update the velocity, which can then be used to update the position. For this lab, we have the F net equals the force of gravity plus the force of the spring. And for this case, we know that F net is going to equal 0. So the force of gravity is going to equal the force of the spring. And then these are just the formulas so that you can see what they equal to. So mass times gravity is going to be K times the magnitude of L minus L0. Energy principle. The energy principle is the change in E equals E final minus E initial. E is equal, for this lab, to the kinetic energy plus the potential energy of the spring plus the potential gravitational energy. Kinetic energy is 1/2 mass times the velocity squared. Potential spring energy is 1/2 KSS squared. And then potential gravitational energy is mg times delta H. So tracker. This is just a little bit of the analysis. So obviously on this side you can see the x's and the y's and how the graphs acted during the tracker analysis. Data for computation. So for this lab, the mass of the unit is 0.402 kilograms. The initial position is negative 0.10606, negative 0.6505, and 0. The initial velocity is the 0 vector, and the time of oscillation is 1.619 seconds. We then can calculate S and L0. Because we know what the oscillation time is going to be, we can use that equation and rearrange it to solve for K. We know the average is going to be 1.619 seconds, so we get that K is equal to 6.83. To solve for the L0, we're going to take the mass times gravity and equals the Ks, and then rearrange that so that we get that L0 equals 0.123. The code. So the first part of the code is going to be just entering the already known values. The second part of the code is going to be getting the length of the stretch spring, which is just going to be the ball position minus the spring's position. And then, of course, calculating the direction of that. And then S mag L minus 0 is just going to be the difference between the relaxed length and the stress or compressed length. So, edit these next 4 lines. So, we're going to have 1/2 the ball's mass times the magnitude of velocity squared. And that's just what the formula for K we know to be. The UG is going to be equal to the ball's mass times gravity times the ball's position at Y, which is just the formula again. And then the potential spring is going to be 1/2 KS times S squared. And then E, of course, is the total of all the energies acting on the system. So before the loop, we just want to go ahead and say what our initials are going to be so that we can use those for later calculations. And then for line 12, we're going to calculate the gravitational force. For line 15, we're calculating the spring force. For F net, we know that's going to be the spring plus the gravitational force, which is going to equal 0 in theory. And then the ball's velocity is going to be updated through this equation, and the ball's position is going to be equal to this. And then this is just reiterating what was in the last slide so that we can calculate the new length and S. So then with the new values, we're going to calculate the K, the change in K, the UG, the delta UG, the US, and the delta US, so that we can calculate the E and the delta E. So the results. The change in energy worked just as it should and had fairly accurate calculations, which was this part. And then the position versus time graph had somewhat similar curves, but the predicted were larger than the analyzed data. So as you can see, this is far more negative than the predicted graph, and this could just be because my center of mass was off and the analytical tracker are just another human error. So what does it mean? Is the energy principle satisfied? So for the energy principle to be satisfied, the total has to pretty much equal 0, and we see that right here. It pretty much followed that trend throughout the whole lab, so that was good. And then what does it mean? Using the data obtained in tracker, make two separate estimates of the oscillation period. So we have T of x equals 1.619 and Ty equals 1.519 with a difference of 0.1. So this could basically mean that there was more oscillation in the y direction because it was going closer to 0 faster than it was in the Tx. So this could just be simply because the force of gravity was pulling on the object harder than the spring was able to snap back because of the Ks. So that's just possibly why that was so much different. And then that is it. So thank you for watching.